Hi everybody. So over the last couple of videos we've begun to look at the Schwarzschild metric, which remember is a very special solution of Einstein's field equations, particularly of the vacuum field equations, and it's for the case where your so-called gravitational field is being produced by a static spherically symmetric mass. So for example, a non-rotating star, and it's valid in the region of space outside the mass. So it can be used to describe, for example, a planet moving in orbit around a star. And that's what we looked at over the last few videos. So we looked at the metric itself, and then we said as a postulate of the theory of general relativity, so as part of the metric theory of gravitation, it's postulated that particles, so whether they be massive particles like planets or whether they be non-massive particles like photons, they travel along the straightest possible path in the curved space-time. Okay, so that's a geodesic. Alright, so particles move along geodesics. So we find in the Schwarzschild metric what the geodesics are over the last couple of videos. We used the geodesic equations to find the trajectory of a massive particle. Okay, so the analysis that we did over the last couple of videos is for massive particles like planets, and we found the so-called orbit equation. That was the differential equation for W in terms of phi, and then we wrote down the solution and we looked at how the orbit compares with the Newtonian theory. So in Newton's theory, the orbits are conic sections, and then in the Schwarzschild metric, it's almost a conic section. But we saw that in the case of planetary orbits, you then get precession. So it's like the ellipse of the planet's orbit rotates. Now, as I say, all of that analysis was only for massive particles. Okay, so we did make an assumption in one place in everything that we did, that the particle moving in the gravitational field had mass, and it was at this point, it was at the point where we used, I'll just write it here as a quick aside, it was where we used the proper time as the parameter for the geodesic. Okay, so remember we used proper time, which is defined like this. So d tau squared is minus ds squared over c squared, and then we used the following relation. So if we just rearrange that, we get ds by d tau squared is equal to minus c squared, and that is actually your Lagrangian. Okay, that's the Lagrangian that you use in the Euler-Lagrange equations to get the geodesic equations. And so in those last couple of videos, we find the geodesic equations for t, theta and phi, but for r, we instead use this. Okay, so we just used L equals minus c squared. But for photons, we can't do that. Okay, because proper time is not defined for photons. Okay, hopefully you remember that from special relativity. Okay, why is it not defined? Because for photons, ds squared is 0 along their path. Okay, so remember again, just think back to special relativity. So just forget about the Schwarzschild metric a moment. Just think back to the Minkowski metric in special relativity. So ds squared is minus c squared dt squared plus dx squared plus dy squared plus dz squared. But along the path of a photon, this is the square, so between two neighbouring points on its path, this is the squared distance between the points. Okay, so dx squared plus dy squared plus dz squared, that's the squared distance. But then dt squared is the squared time, and c squared is the squared speed of light. Okay, so what happens is, because the photon actually does travel at the speed of light, this whole thing is 0, okay, for a photon, because this is distance here, and this is speed times time, which is distance. Okay, distance is speed times time. So for a photon, that's 0. So ds squared is 0 along a photon's path. And the same will still be true in general relativity. Okay, so whenever we go to find the equations of motion for the photon in the Schwarzschild metric, we can't use proper time as a parameter, and we have to do something else. So that's what we're going to look at now. We're going to look at the geodesic equations for the photon motion and see how the path of a photon looks in the Schwarzschild metric. Okay, so what you can do is, instead of using the proper time as your parameter, you just keep a general parameter u, okay, which only has really mathematical significance rather than physical significance, okay? So I'll say for photons, we can't use proper time tau as a parameter. So just use a general parameter u. Okay, and then you can go through the same steps of writing down the Lagrangian, okay, which will now just be ds by du squared, and it will have the same form as before. So this will be minus 1 minus 2 gm over c squared r c squared t dot squared. Okay, so remember, you just take the metric, and everywhere you have a differential, you change it to a coordinate with a dot. That's how you get the Lagrangian. Plus 1 minus 2 gm over c squared r to the minus 1 r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. Now, if you go through all the steps of this, of now finding the geodesic equations, you will actually get the same equations that you got for the massive particle, at least for the t, theta, and phi coordinates. Okay, so let's just write them down. Okay, so geodesic equations for t, theta, and phi coordinates are identical to what they were for the massive particle. Okay, so let me just copy those down again. So for t, you get 1 minus 2 gm over c squared r t dot is equal to a, which is a constant. For theta, you get theta double dot plus 2 over r dot theta dot minus sine theta cosine theta phi dot squared equals 0. And for phi, you get r squared sine squared theta phi dot is equal to b, which is another constant. Okay, so those are identical. But then the difference comes in when we go to get the equation for r, okay, the geodesic equation for r. But remember, we do the same trick as we did for the massive particle, where rather than getting the geodesic equation explicitly from the Euler-Lagrange equation for the r coordinate, you just use something about the Lagrangian, okay? And in this case, it's not L equals minus c squared anymore, okay, because this isn't the proper time here. It's just L equals 0. Okay, so why is that? Because for a photon, ds squared is 0. So for a photon, along its path, ds squared equals 0, and therefore also the Lagrangian is 0. So we just get 0 is equal to minus 1 minus 2 gm over c squared r times c squared t dot squared plus 1 minus 2 gm over c squared r to the minus 1 r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. And now what we can do is take this equation, and just as before, we start putting these things in. Okay, so this equation you can rearrange to get t dot on its own. Okay, so t dot is a divided by 1 minus 2 gm over c squared r, so you can put that in here. You can do the same thing for phi, okay, so for phi dot rather, so phi dot will just be b divided by r squared sine squared theta. You can put that here. And let's combine a couple of steps. Look at this equation, okay, and remember what we did last time for the massive particle. We made the assumption that it starts out in the plane theta equals pi over 2, okay, the equatorial plane. And we showed that if it starts there, because of this equation, it has to stay there. Okay, and we can make the same assumption here for the photon, because it's the same geodesic equation for theta. So we can just assume, quite freely, that the photon moves in the plane theta equals pi over 2. Okay, and that will mean for all time, okay? It stays on it. So then theta dot is always 0, and sine theta is always 1. Okay, so let's combine a few steps. So this equation will now become 0 equals minus, now let's combine some stuff. Okay, we've got t dot squared. So that will be a squared over 1 minus 2gm over c squared r, all squared. Okay, so one of those all squareds will cancel this, so you will have minus c squared a squared. I'll write it like this, 1 minus 2gm over c squared r to the minus 1. Okay, so there's a minus sign there in front. Okay, next term, let's just keep that one, so plus 1 minus 2gm over c squared r to the minus 1 r dot squared. This term is 0 because theta dot 0, and then this term will just be r squared. Sine theta is 1, phi dot will just be b over r squared because sine theta is 1, so phi dot squared will be b squared over r to the 4. So when you multiply by this r squared, you just get b squared over r squared. Okay, and now let's bring that up here. Okay, so let's bring this up here, and let's keep this term, let's bring this term to one side. So we will have, therefore, r dot squared, so let's do a couple of steps at once. We'll also divide through by this factor. So we will have c squared a squared minus b squared over r squared times 1 minus 2 gm over c squared r. Okay, and that, did I get it right? Just double check. Yes, okay, and that is the equation of motion for a photon in the Schwarzschild metric. Okay, so again, along its path, it's confined to the plane theta equals pi over 2. So along its path, it has an r coordinate and a phi coordinate, essentially. The r coordinate satisfies this differential equation, okay, and this, remember, is differentiation with respect to u, just the general parameter, and the phi dot comes from this differential equation. Okay, so phi dot equals b over r squared. But once again, rather than having r and phi as functions of u, it would be preferable just to have r as a function of phi. Okay, so in other words, find the orbit equation. So we can do that by introducing, once again, w equals 1 over r, or r equals 1 over w. And then if we want to put that in here, we need r dot. R dot is just dr by du. And using the chain rule, that's just dr by dw, dw by d phi, d phi by du. Dr by dw is just minus 1 over w squared. And then you have dw d phi. D phi du, that's just phi dot. And phi dot from here is just b over r squared for theta equals pi over 2. Okay, so phi dot is b over r squared, or in other words, bw squared. That cancels that, so this is just minus b dw d phi, same as it was for the massive particle. Plug this in here, and you get b squared. dw by d phi squared is equal to c squared a squared minus b squared w squared. Let's just, well, we'll keep it like this. So open brackets, 1 minus 2 gm over c squared w. And let's then divide through by b squared. So we have dw by d phi squared is equal to c squared a squared over b squared. And then we'll multiply out this bracket also. So we'll have minus w squared plus 2gm over c squared w cubed. And finally now we have a differential equation for w in terms of phi. Okay, and if we can solve it for w, then we can get r just straight away from here. R is just 1 over w. But once again, we have a differential equation that we cannot solve. So we do the same thing as last time for the massive particle. We differentiate this differential equation with respect to phi, okay? Which makes it into a second order differential equation, yes, but it turns out that's easier to handle. So differentiate with respect to phi, and you get, on the left-hand side, using the chain rule, 2 dw by d phi, and then times d2w d phi squared. On the right-hand side, this is a constant, so it's gone, and then you have minus 2w dw d phi plus 6gm over c squared w squared dw d phi. Okay, just using the chain rule there everywhere. And lastly, we can cancel dw by d phi here, here, and here, so long as we assume it's not a circular orbit. Okay, so we're assuming that dw by d phi is not 0 everywhere. So it's not everywhere 0, okay? It's non-zero, at least somewhere. So there is dependence of w on phi. And we'll also divide by 2, so that goes, 6 becomes 3. And we'll bring this term over here. So we get, in the end, d2w by d phi squared plus w equals 3gm over c squared times w squared. And that is the orbit equation for a photon. Okay, so it looks similar in shape to the orbit equation you get for the massive particle, but not exactly the same. And actually, it's a little bit easier, just slightly easier to solve than for the massive particle. Okay, so the algebra is just a little bit simpler, so we're going to take a look at that now. Okay, so I've just erased the board and moved the orbit equation up here. And now we're ready to go ahead and solve it. And in fact, to do that, what we can do first of all is solve it for the case where capital M goes to 0. Okay, now why would we want to do that? Because, first of all, this term on the right-hand side will disappear, which simplifies things. But this particular case, for m equals 0, this corresponds to where the gravitating mass, okay, so the mass that's generating the gravitational field, so like the sun, disappears. Okay, so it means we're switching off the gravitational field. Okay, so i.e. no gravitational field. And what we should expect in that case is that the solution is a straight line. Okay, if there's no gravitational field, then the space-time isn't curved, and we would expect the photons, the light, to just move in a straight line. Let's see if that's the case. So for m equals 0, our orbit equation just becomes d2w by d phi squared plus w equals 0. And hopefully you recognize that as the equation of simple harmonic motion. So the solution is w equals, now there are different ways of writing it, so you can write it as a linear combination of sine and cosine, but I'll just write it like this. So a constant times sine of phi minus or plus phi 0, where phi 0 is just some constant angle, some phase. So that's the general solution for m equals 0. Now, the constant phi 0, I can just choose that to be 0. It's okay to do that because phi 0 really here, it just corresponds to an orientation, okay, of the axes essentially. So I will just freely choose phi naught equals 0. So w is just a sine phi, where a is a constant, and so r, the radius, is 1 over w, which is 1 over a sine phi. So there you are. There's r as a function of phi. Is it a straight line? Might not be obvious, but yes, it is a straight line, because if I multiply through by sine phi, I get r sine phi equals 1 over a, where a is a constant. Okay, but r sine phi is just y. Okay, so remember here we're in polar coordinates, in the plane theta equals pi over 2. Okay, so in that plane, x is equal to r cos phi and y is equal to r sine phi. So yes, the path of the photon is just a line where y equals constant. So it's like this. If I draw x, y, it's just a line where y equals constant, okay? Y equals 1 over a. And if the photon initially is at phi equals 0, okay, then the radius will be infinite. Okay, if you put phi equals 0 here, you get r equals 1 over 0. So initially at phi equals 0, which means here, the photon starts infinitely far away. So it's coming out from infinity, it's coming in like this, and it's going all the way over here. So this is the direction of motion of the photon, like so. So, fine, that's the solution for when you switch off the gravitational field, a straight line. Perfect. But what happens then if we don't switch off the gravitational field? Okay, so let me just draw a box around that. Well, if m is non-zero, unfortunately, we cannot solve this equation exactly. So we use the same trick that we did for the massive particle, although I didn't show all of the details, and I won't show all of the details here either, because it's a wee bit complicated, and it's not something I would expect you to be able to do completely on your own on a test or on an exam. So what you do is you assume that the effect of having this term, okay, of having the gravitational field, you assume that it's a small effect. Okay, so we expect that the light ray is going to be not a straight line anymore, but deflected from a straight line, but we assume that the deflection is small. Okay, so the effect of general relativity is a small effect. Okay, and indeed that will be the case. Look, you've got a c squared in the denominator here. So this is a small correction, a small term on the right hand side. So that means our solution, we can take a perturbative approach. So we assume that our solution for W is almost still this, okay, but just with an extra small correction. So what we do is we assume that W is equal to W0 plus W1, okay, where W0 is just this, what we had before, the undeflected straight line, and then W1 is just a small correction. And skipping some of the details then, if you take this and plug it in here, okay, you will end up with a differential equation for W1, and you keep everything to lowest order in W1 over W0 because you assume that W1 is a small correction. At any rate, the solution that you end up with is, and I'm just going to copy it here, is the following. So you get W equals, let me just see now, A sine phi, so that's the W0 part, plus 3gm over 2 c squared a squared 1 plus a third cosine 2 phi. Okay, so that's the solution that you will get ultimately. Now, what we can do is find what the value of the, let me just check this again. Okay, so what we can do is find what the angle is for infinite r. Okay, so again, we said in the undeflected case, your photon is a straight line. Okay, so when it's initially, when the photon is far away, r equals infinity, the angle is 0. Okay, but now I'm saying with the gravitational field switched on, we expect the photon to be deflected. Okay, it's going to curve actually a little bit, okay, around the mass. So at the infinite r, at the start, the angle will not anymore be 0, it will be something different, okay? So when we switch on, let me draw it in a different colour, when we switch on the gravitational field, so we put our mass m there, we expect that the photon is going to go something more like that, okay? So it follows a curved path. So really, you know, if I draw just a dotted line here, and essentially it's asymptotically approaching this ray. There's a little angle here which I could call phi infinity, and it's the same over here. So we're trying to find that angle. So when r is very large, what is that angle of deflection? And when r is very large, that means w is 0. So I'll say as r goes to infinity, w goes to 0, and phi goes to phi infinity. So let's find phi infinity. So if we put w equals 0, we get 0 equals a, and then we have sine of phi infinity plus 3gm over 2c squared a squared 1 plus a third cosine 2 phi infinity. And again, we will assume that the deflection is small. Okay, we assume this is all a small effect, so phi infinity is a small number. So we can use the Maclaurin series for sine. Okay, so approximately this will just be phi infinity, and as for the cosine over here, that will just be approximately 1. Okay, so making those lowest order approximations, we get therefore 0 is equal to a times phi infinity plus 3gm over 2c squared a squared times 1 plus a third, which is 4 thirds. Okay, and that 3 will cancel that 3, and 4 divided by 2 is just 2. So therefore, we have, if we take, let's see now, well, there's an a there and an a there, that will cancel as well. So in the end, we get phi infinity equals minus 2gm divided by c squared a. Okay, let me just check I got that right. Yes. Okay, so that's the angle of deflection here. Okay, so that's this small angle, and it is small. Okay, so c squared on the bottom line, it's a small deflection. And remember here that 1 over a is this distance of closest approach, okay, in the undeflected case. Okay, so in the undeflected photon, 1 over a is this length. It might be interesting to see what this length is now. Okay, so when you switch on the gravitational field, the distance of closest approach gets a little bit less. Okay, but it still happens on the y-axis here, so it still happens at phi equals pi over 2. So we can try to find the value of w, or the value of r, when phi equals pi over 2. So let's just do that over here. Okay, so when phi equals pi over 2, we have w equals a sine pi over 2, which is just 1. So a plus 3gm over 2 c squared a squared, and then times 1 plus a third cosine of 2 pi over 2, so that's just cosine pi, which is minus 1. So 1 minus a third is 2 thirds, so that's just 2 thirds, and that'll cancel that 3 over 2. So we just have w is equal to a plus gm over c squared a squared, and that's just factorising it out. A times 1 plus gma over c squared, and then if we change it back to r is just 1 over w, so that's 1 over a 1 plus gma over c squared, and we can actually use the binomial theorem here. So if we keep that 1 over a factor here, and again we've got, essentially here we've got 1 plus gma over c squared to the power of minus 1. So the binomial theorem to the first order term will just give us that this is approximately equal to 1 minus gma over c squared. And look what we have. Okay, so in the undeflected light ray, the distance of closest approach was 1 over a, and now this is the distance of closest approach in the deflected light ray. Okay, and it's not the same as 1 over a. Okay, in fact it's less than 1 over a, because you've got 1 over a times something less than 1. Okay, 1 minus something. Okay, although this something is only a small amount. And so that is this is what the path of a photon looks like in the Schwarzschild metric. Okay, so when there's no gravitating mass, you get a straight line, as you would expect, no gravitational field. But when you switch gravity on, you just get a deflected light ray, like so. Okay, so the light ray comes in a little bit closer at its point of closest approach, and it's deflected away from the straight line by this little angle phi infinity, which again, it's a small deflection. Okay, so in the next video, we're going to be thinking a little bit more about light, I suppose, in the context of black holes.